Hello and welcome back to our subject, Advanced Digital Technique. Our discussion for today is about Arithmetic Logic Unit, or we call it the ALU. What we have here is the block diagram of the hardware components of a computer. Now, as we all know, the hardware components of your computer contains the input device, the central processing unit or CPU, the main memory, the auxiliary memory, and your output device. Now, your CPU contains the so-called arithmetic logic unit, which is the focus of our study this morning or this day, and your control unit or CU. So basically, your control unit here is the one that controls the transmission of your signal from one area of your computer to another area of your computer. Meaning to say, from your input device going towards your central processing unit, the data will have to be controlled by your control unit. So siya ang magbuot kung kano sa siya i-allow nga isulod sa imong central processing unit. At the same way, it is your control unit that allows the transmission of data from your CPU going towards your main memory or going into your auxiliary memory or going to the output device. Okay? So that's the main function of your control unit. Again, it controls the transmission of data from one area of your computer to another area of your computer. So, ang atong discussion sa whole semester on this particular subject will be focusing more on the ALU and the memories, no? The main memory, no? What are the content or how does main memory works, no? That would include also the principle on using your auxiliary memory. Okay? So that will be our focus on this particular subject. Let us define what is arithmetic logic unit or ALU. ALU is the section of the computer that carries out arithmetic and logic operation. So it is where arithmetic operations and logical operations are being performed. Okay? Now, one basic example or one basic circuit which can be found inside your ALU is the half adder. The half adder is defined as a logic circuit that adds 2 bits. So when you say bit, that could be either 1 or it could be 0. So there are 2 binary bits, 1 or 0. So basically, half adder can add only 2 bits, no? Either 1 or 0. So what we have here is a logical circuit of a half adder. This one here. Okay. Now, the logic circuit contains the exclusive OR gate and AND gate. The exclusive OR gate is represented by sum as its output, and for the AND gate, the output is represented by the word carry. So there are two inputs here represented by input A and input B. Now, from your previous discussion, or from our previous discussion, I mean, when you say exclusive OR gate, that means that the output of an exclusive OR gate will be equal to 1 if the number of ones in the input is odd number of ones. In your AND gate, the output will be equal to 1 if all inputs are high or all inputs are 1. So let's try to see the table here, no? The table of your half adder. So you have here input A and input B. The output is represented by the sum, which is the output of your exclusive OR gate. And we have another output, which is your carry, which is the output again of your AND gate. Now, if both inputs are 0, then the sum is 0 and the carry is also 0. No? Again, based on our definition of exclusive OR gate, the output will only be equal to 1 or high if the number of ones are odd number of ones. So here, if you notice that if A is 0 and B is 1, odd number of ones, so the output here for your sum exclusive OR is 1. Then you have inputs here 1, and then B is 0, again odd number of ones, the output is 1. Now if both A and B are 1, that means that the number of ones in the input is even number of ones. So that is why our output will be 0. So that is the output of your exclusive OR gate, which is represented by sum in the output terminal. Now for the carry, which is represented, or the carry which is the output of your AND gate, the output is this one here. So again, if we will review our definition for the AND gate, the output will only be equal to 1 if all inputs are high or 1. That is our half adder. Another circuit which can be found inside your arithmetic logic unit is the full adder. Full adder is defined as a logic circuit that can add 3 bits. So kaganiha, ang half adder, 2 bits lang ang pwede niyang i-add. Ang full adder, 3 bits ang pwede niyang i-add. Okay, so this one here is the circuit of your full adder. So if you notice that it contains an exclusive OR gate and a combination of AND gate and or 3 AND gates and an OR gate. So if you notice that the input of your OR gate is connected to the outputs of your 3 AND gates. Okay? So again, the output of your exclusive OR is represented by sum, and the output this time of your OR gate is represented by carry. Now, let us consider this table here, the truth table of your full adder. So this time we have 3 inputs represented by A, B, and C. Again, the output is sum and carry. Now, let us take first the output of your exclusive OR, which is represented by the sum at its output terminal. Now it says, again, if the number of ones are odd, like this one here, 0, 0, 0, 1, the output is 1. 0, 1, 0, odd number of ones, the output is 1. But here, 0, 1, 1, the number of ones are even, so the output is 0. 1, 0, 0, the output is 1. That's odd number of ones here. And then you have 1, 0, 1. The number of ones are even, so the output is 0. And then you have 1, 1, 0. Again, the number of ones are even, so 0. And then we will add here 1, 1, 1. The output here will be equal to 1. Okay? So that will be the output of your exclusive OR gate. Okay? Now, how about the output of your carry? So we know that in our definition, the carry here, which is the output of your OR gate, as a review, OR gate means what? The output will be equal to 1 if any of the input is 1 or high. So how do we obtain the output of your carry? So we can obtain the output of your carry by substituting the value of your A, B, and C. For example, in the first condition, you have A is 0, B is 0, and C is also 0. So you have here 0, 0, and C is also 0. Okay? So that means that this line here, which is connected to 0, this one here, going here, that means that this one here is 0. And this line here, going here, is also 0. Okay? And this line here is also 0. And the input here will also be 0. And so as the input here will also be 0. So AND gate, 0, 0, the output is 0. So this is also 0 here, and this is also 0. So the output of your carry will be equal to 0. Okay, so that is our carry here. Okay, so if the input is 0, 0, 0, the carry is 0 based on the traced value of your circuit. So let's change the condition. Let's say 0, 0, and 1. That means that C is 1. Okay? So the new value of your C here is 1. So that means that this line here will be equal to 1. Alright? So we will erase first the value of 0 here. Okay. And this one also. Alright. So you have 0, 0, 1 as the value of your input. So again, this line here will be equal to 1, and this line here from here is 0, 0, 0, 0, 1, 0, 0. So what will be the output of your AND gate? This one here. Okay, so you have 0, 0 for AND gate. The output is 0. Then this one here again is 0. 0, 1, the output is 0. Okay, here, since C here is 1, okay, let us change the value. Okay, and this one here is also, this is 1. Okay, and this one here is 0. Okay, so you have 0, 0 also as the value of your, no, this one here is 1. I'm sorry. So this is 1. Okay, so you have 0, 0, 0 is 0. Then you have 0, 1 is still 0. Then 1, 0 is still 0. So the output of your OR gate will still be 0. Okay? So that is why we have here in the carry, if the value of your input is 0, 0, 1, the output remains 0. Okay? So let's change the value of your A, B, and C. Let's say the value of your B now is 1, or the value of A is 0. Then the value of your B is now 1. Okay? And then C is 1. So that means that if this B here is 1, if A here is 0, that means that the output here remains 0. But this particular case here, this one, we will change this with 1. Okay? So this is now 1 because B here is equal to 1 connected to B. So the input of this AND gate is 1, 0. How about this AND gate? This one. What is the input? So you have the value of your A is still 0 here, and then the value of your B is now, the value of A is 0, and the value of your C is 1. So you have 0, 1, the output will still be 0. But in this case here, your B is now, let me erase this one. The value of your B now is equal to 1. Okay, so from here, the value of your B is 1, and the value of your C is also 1. Okay, so if your input is 1, 1, that means that if your input is 1, 1 again, the output means equal to 1. Okay, so if the AND gate is the input of the AND gate is 1, 1, the output is 1. Okay, based on our definition of an AND gate. So the input now of your OR gate is 0, 0, 1. So based on our definition for the OR gate, if any of the input is high, okay, if any of the input is high, the output of your AND gate is high. Okay, so now you have 0, 1, 1 as your input. The output is 1. Okay? So, ingon na ang pagkuha na to sa tuang carry. So, if you have, for the last value, 1, 1, 1, okay? So, automatically, your output here will be equal to 1 also. So, that is the truth table for our full adder. And we have to remember the table for the half adder and the full adder so that we can apply that in our next circuit that we will be discussing. So what we have here is a binary adder. So a binary adder is a logic circuit that can add two binary numbers. So what's the difference between binary numbers and binary digit? So when you say binary digit, that is either 1 or 0. Whereas when you say binary numbers, it contains two or more binary digit. Okay? Now, what we have here is a block diagram of a binary adder. Ngano naka-block diagram siya? Because it contains half adder and 3 full adders. This is for a 4-bit binary adder block diagram. Okay, again, it contains 1 half adder and 3 full adder circuits. So, kung ato ni siyang i-draw ang circuit equivalent niya, atong i-interconnect tong half adder circuit, the output of which is the carry, is connected to one of the input of your full adder. And the output of this full adder, the carry of which is connected to another input of full adder, the second full adder, and so on. So this is murag medyo kung ato ni siyang i-interconnect, murag medyo madugo kayo ang ato ang circuit connection, no? Then daghan kayo ang circuit nato, no? So dili masulod sa ato ang i-discuss karon nga area sa ato ang discussion. Okay, so that is why I represent it only using the block diagram. Now, the half adder has inputs represented by A sub 0 and B sub 0. Okay, duha ra makabog input sa imong half adder, right? Then for the full adder, you have inputs A1, B1, and C sub 2 or C sub 1 here. A1, B1, and C sub 1, which is the carry of your half adder. And the output is represented by S1, which is the sum. S1. For half adder, the output here is the sum is represented by S sub 0. And then the next full adder, one of the input again is your C sub 2, which is the output of your full adder. It is connected to your next full adder. So the input now will be represented by A sub 2, B sub 2, and C sub 2, which is the carry of your previous full adder, and so on. So this one here again represents a 4-bit binary adder block diagram. Now, how about if you have 8 bits? Binary adder. So, how many half adder do we need? And how many full adder do we need? So when you say 8 bits, that means that it has to be represented by 1 half adder and 7 full adders. Okay? Now, most of the computer now is 32 bits or 64 bits. That means that for a 32 bits, you need only 1/2 adder and 32 full adder. For 64 bits nga computer, you need 1/2 adder and 63 full adders circuit which are interconnected together. So imagine ninyo na kung pila ka buok AND gate, pila ka buok OR gate, and pila ka buok exclusive OR gate ang ma-involve anang a particular na circuit. And it is only placed in one IC called the Central Processing Unit, wherein ALU and CU is located. Okay. Now, this table here is actually a table of your half adder, and this one here is the table for your full adder. Okay, we will use this as a guide for us to be able to discuss properly the outputs and the inputs of the binary adder block diagram. Okay, so since the binary adder definition says it adds two binary numbers. So let's say our binary numbers are represented by A3, A2, A1, and A sub 0, which is actually the input of your binary adders circuit here, which is here you have A3, then you have A2, then you have A1, and you have A sub 0. And then another binary number is represented by B3, B2, B1, and B sub 0, which is located here. B3, B2, B1, and B sub 0. Okay? The output of this equation, after adding the two binary numbers, the result will be the sum SO, the sum S1, S2, S3, and of course, if there is an end around carry, we represent it with C4, or the carry for the last full adder. Okay, so where can we find SO, S1, S2, S3, and C4? It's here. No? SO, S1, S2, S3, and the carry C4. Okay, so these are the output representation of your binary adder. SO, S1, S2, S3, and C4. If there is any other, if there is carry after adding it. Okay. Now, suppose we want to add 12 plus 9. No? I-press nimo ang 12 sa imong keyboard. And then, plus 9 sa imong keyboard. So, this 12 will be converted into its binary equivalent from electrical signal into its binary form, which is, in this case, 12 is 1100. Okay? So, please try to recall your binary conversion, no? Decimal to binary conversion. Then 9 will be represented by 1001 in binary form. So once you add this one, you have 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1, and 1 plus 1 is 0 with a carry of 1. So bring down 1 here. So the answer is 10101, which is equivalent to what? This is 1, 2, 4, 8, 16. 16 plus 4 is 20, plus 1 is 21 in decimal number. Okay, now, let's try if this answer here is the same if we will use this circuit here, the binary adder block diagram. Okay, so the first value, A sub 0, this is your A sub 0 here, and this one here is your B sub 0. So let's add the two number. So you have A sub 0 is 0, and B sub 0 is 1. Okay? According to our half adder, if A is 0 here, and B is 1, 0, 1, the output of your, or the sum is equal to 1, and the carry is 0. So according to your half adder table, the sum is equal to 1 and the carry is equal to 0. Okay? So that will be the result, no, of your adding 0 and 1 in your half adder. Again, the sum, SO, is 1 and the carry is 0. Okay? So, next is A sub 1, B sub 1. Since carry C sub 1 here has already a value of 0, so what will be A sub 1 and B sub 1 equal to? So, this one here is your A sub 1. This one. And your B sub 1. So, that means nga, 0, 0 ang value. So, B sub 1 is 0. And A sub 1 is also 0. So, in other words, the inputs for the full adder will be A sub 1 is 0, B sub 1 is 0, and C sub 1 is also 0. So what will be our output? So based on our full adder truth table here, A is 0, B is 0, C is 0, the output of your sum is 0. Okay? So the output of your sum is 0. And then the carry is also 0. So the carry here will be also equal to 0. That will be your output S sub 1, 0. And the carry C sub 2 is 0 also. Okay? The next is A sub 2, B sub 2, and C sub 2. Since C sub 2 have already a value, then you will get the value of your A sub 2 and B sub 2, which is in this case 1 and 0. So, we write down the value here. The value of your A sub 2 is 1. Okay? And B sub 2 is 0. Okay? So, the value now of your input for the full adder is what? 1, 0, 0. And what is 1, 0, 0 here? 1, 0, 0. The sum is 1 and the carry is 0. So, the sum is 1, the carry is 0. Okay? Then, the next value is B sub 3 is equal to 1, and A sub 3 is equal to 1, and B sub 3 is also equal to 1. So, we will write down the value. A sub 3 is equal to 1. B sub 3 is also equal to 1. And then, the carry is 0 here. So, what will be our output? You have A sub 3 is 1, 1, 0. So, where is 1, 1, 0? This one here is 1, 1, this is for the half adder. So, the answer is here, no? 1, 1, 0. Okay, so 1, 1, 0. The sum is 0. And the carry is 1. So again, the sum here is 0 and the carry is 1. So what will be the final answer? The final answer will be 1, 0, 1, 0, 1, which is the same as your answer using the column by column method of addition. Okay? So pareha sila og answer. In other words, this particular binary adder circuit performs binary number addition. Okay? So ingon ana siya. Dili ni siya literal nga nag-add og two binary numbers, pero gipaagi niya using logical circuit. So ingon ana ang iyahang pag-perform sa sulod sa imuhang ALU. In other words, ang computer itself dili na siya ingon nga literal nga nag-add og two numbers. Iyang gipaagi sa logical circuit ang iyahang pag-perform para makuha niya ang output, which is in this case 10101. Okay? So that is how binary adder works.